Let's revisit the last lecture quickly. We were studying radiations from linear antennas. So, in phasor form, we saw that the potential can be computed from this equation. And in the far field, when this factor approaches infinity, this can be approximated as where, if let's say here is the current distribution, so this is R prime and this is R, and the unit vector n is in the direction of R, and this is R minus R prime. This is our observation point. And then we solve this problem for a linear center fed antenna. The current distribution like this. Oriented along z-axis, and we found the potential A of R, and then we found that the time average Poynting vector can be written as like this. And the magnetic field, which is given by this, can be approximated by this thing, and the electric field, which we can find from this equation, can be approximated as, we can replace this thing with minus iota kn, iota cancel, so we have minus k n cross b, and if I, let's say, write this k as omega mu naught epsilon naught square root, omega cancels, and one square root, this thing cancels with one of its square root, and the other is c, so minus c n cross b. This is in far field, and this is exact. This is exact, and that is in far field. We found that the angular distribution of power is defined as the radially outward component of time average Poynting vector which can also be written as like this. This B is this, so this is A. So you can either write it in terms of B or N cross A. It's the same thing. And for the linear antenna, we saw that this angular distribution of power comes out to be equal to this. Z naught So last time when we left, we were discussing special cases of the antenna. So the antenna is like this. This length is D. So the first case that we took, and this is Z-axis. Okay. So let's say this is the point where we are observing the field. This distance is R. This is the direction of unit vector N. So the first special case we discussed was of a small dipole, that is D is much smaller than wavelength. So when KD is much smaller than wavelength, we can approximate this cosine function as 1 minus this thing square root, और square root को फिर आप टेलर सीरीज से ओपन कर लें. So just as a side note, ये अक्सर approximation यूज होती है. Let's say small y, sin y is approximately equal to y, and cosine y, which is 1 minus this, and 1 minus half sine square y, and higher term, which we can approximate as 1 minus. So this sine y can be approximated with y, so this is y square. So for small argument, cosine can be approximated with this thing. So if you make the approximation here, 1 cancels with 1, and if you combine the rest, the angular power distribution is this thing into sine square theta. And if I plot it using polar coordinates, so this is z-axis, this is whatever, this is xy plane. So angle theta is this angle. So at theta is equal to 0, in this direction this function is 0. At theta is equal to 180, this function is 0. So the power is 0 here and 0 here. So in polar plots, the magnitude is represented by the distance of a point from the origin. So it is 0 here, so the point here is point here. At theta is equal to 90, this is maximum, so the point is here. So for other thetas, and since it's independent of phi, on both sides it's like this. So the way to read this plot is this. If you want to see what's the magnitude of relative magnitude of this function, let's say in this direction, you see what's the length of this line. So here in this direction, if it is like this, in this direction it is larger, in this direction it's smaller. As you change direction, it's getting smaller, so it's 0. If you make the line plot, this should be like this, right? Theta 0 to 180 degree. You get 0 at 0 and 0 at 180. So instead of line plots in antenna community, people prefer the polar plot because this is a better visualization of the radiation pattern. If this is the dipole, there is more power being radiated in this direction, and there is 0 power in this direction, and power gets smaller as you change the direction. Let's take another special case, which is very important. Now let's say this special case of when the length of the antenna is half of the wavelength. So when D is equal to, this is usually called half wave antenna. So when D is lambda by 2, KD is, this is lambda by 2, lambda cancels 2 cancel, this is pi, and this is pi, cosine pi is -1. So this becomes pi, and you can use a vector identity to you can use a half wave, half angle identity, and dp by d omega becomes cosine square pi by 2 cosine theta over sine square. And the polar plot for this function is like this. This actually, these balloons becomes thinner, which means that the power radiated in this direction is now much more relative to the other directions than this case. So that's why this half wave antenna is very popular, that most of the power is being radiated in a particular direction, radially outward, perpendicular to the antenna in this plane. So if this is the antenna, most of the power is being radiated in this plane. The power is going first of all in all direction equally in this plane, but it's stronger here than in this direction. You can take another case, let's say D is equal to lambda, when it's called full wave antenna. When D is lambda, this becomes, sorry, I didn't put this 2 here, the 2 here. So this is lambda by 2, this becomes pi by 2. So this is actually even easier. This will be 0, and this is pi by 2, so you get right away that. So when d is lambda, kd by 2 would be pi. And then this function is four cosine power 4 pi by 2 cosine theta sine square theta. So the plot of this one is like this. Let me draw it on top of it. This is even more directive than the half-wave antenna. Some people like to imagine this half-wave antenna as a superposition of two full-wave antennas, and because of this superposition, there's more power along the radial direction. Okay, so in the notes I have given an example for D 3 by 2 lambda as well. The important thing is that the length of the antenna depends on the wavelength. If, for example, you are transmitting FM radio. FM radio has a frequency of about 100 megahertz. So what's the wavelength for 100 megahertz? F is 100, 10 power 3 meters. So half wave would be 1.5 meters. You need a pretty small antenna. Okay, so most radios have an antenna that can stretch. It's of the order of meters. So if it is smaller than this, the efficiency would reduce, but it would still work. Okay, so this gives you a ballpark number. If you are transmitting, let's say, AM radio stations, AMs work from anywhere from, let's say, 1 kilohertz to 100 or 1000 kilohertz, so let's say 1 megahertz. So at 1 kilohertz, lambda is (1 into 10 power 3). This is 3 into 10 power 5 meters. And at 1 megahertz, this is 300 meters. So even half of this is like 150 meters. Half of this is still 100 kilometers. Okay. Has anyone of you been on GT Road near Rawalpindi, and you pass by Rawat, and you see extremely large antennas on your right side? You actually don't see antennas at all, because the wires are so high that we can't see those wires. But we do see those supporting wires, because there are large towers, big towers, and the towers have to be supported, so there are a lot of wires going to ground. They are just supportive wires. So we do see those supportive wires, and we see large poles. So it's like I think you can put 100 LUMS campuses, maybe more, in the region of those antennas. So the antennas are literally kilometers long. That, when that station was built, the transmitting station, that was one of the biggest in Asia. It used to transmit AM radio channels to the other side of the earth as well, to Africa, to South America. It doesn't work anymore because people don't need it, right? There are FM station and you can transmit radios through no internet. So the idea is to tell you that the antenna length is critically dependent on the wavelength for efficient transmission. As you go to higher frequencies, like let's say a gigahertz, where our mobile phone works, the wavelength comes down to centimeters, so we can use small antennas in our mobile phones to communicate and so on. Yeah, but actually the ballpark number is lambda. Like 1 lambda, 2 lambda, lambda half, it's the same thing. Okay, so let's now move from specific current density to an arbitrary current density. Let's say we have a current density that is unknown to us completely, but we do know something about it. So it's not completely unknown, but we do know something. So the question is, what we can say about its radiation pattern. To characterize an arbitrary current density, or you can say a more complicated, if let's say you know the current density, but the current density is too complicated, that you can't really perform this integration. So if you know exactly the current density, in principle, you can go through all of this, solve the integral and find the radiation pattern. But let's try to come up with a method that we can get a fairly good idea based on just a part of the information about the current density, instead of knowing fully about the current density. And for that, we have to go towards what is referred to as multipole radiation. So unfortunately, we won't be able to do this topic in detail because we have only today's lecture dedicated for this. So in principle, we can do a multipole expansion of that integral in spherical, cylindrical, and let's say Cartesian coordinates. But we will do it in just one, let's say Cartesian coordinates system, one type of multipole radiation, and we will concentrate on the first couple of terms. We can also similarly do, let's say, expansion in terms of spherical multipoles, and then discuss spherical term distributions. But let's concentrate on a simple multipole radiation pattern. So for that, we have the far field radiation pattern given by this expression. So this exponential term, we can make a Taylor series for this and substitute that here and get a series solution for this function. Now the Taylor series for this thing is don't confuse this n hat. This n hat is actually r hat. I think I should have used this symbol, but we have started with this. And this n is the index of summation for this series. So you can expand this thing in Taylor series like this. And for example, for a special case, when your n hat is x hat, this simply becomes x. So exponential iota kx. And we already know that the series for exponential iota kx is like for exponential x, for example, x power n, and then this would be x. So this becomes the series for the exponential. We can, if I open it, n0 term would be 1. For n1, this becomes plus iota k n hat dot r. For n2, this becomes iota k square over 2 and so on. So this is the series. So if we substitute this thing here, the potential in the far field becomes sum over n. Now this thing is independent of r prime, so I can take it out of the integral. And in the integral we have n dot r power n d2 bar. So in principle, this has infinite number of terms. But you see that as n increases, the terms decay as 1 over n. For example, this term is proportional to 1. This is proportional to still 1, but this is 1 over 2. The next term would be 1 over 6. The next term would be 1 over 4 factorial, and so on. So the contribution of each term would keep on decreasing. So the first term, or the 0th order term, if we concentrate on that, the 0th order term is just this. For n0. Now let's see what this term is. We can integrate it by parts. Let's imagine 1 with it. And if you feel easier, you can think of it as jx, jy, jz. This is a vector. You can integrate each scalar term individually. So if I do it just in this form, the integral of 1 is, if it is integral over x, this is just x. So if it is y, when integration is over y, it's just y. When integration over z, it's just z. So essentially something like this. R, I, R, J, K, and the current as it is. Okay? And the integration is from minus infinity to infinity. Minus I can write it in vector form, something like, if I just put R, this becomes diagonal. So anyway, so there's R vector here, and then there's a derivative of this thing, which for vector form is this thing, the derivative with respect to R prime, integration over this. Now this term will be 0 if this J is finite. Finite meaning that it occupies a finite volume in space, because it is then 0 at minus infinity and 0 at plus infinity. So in that case, this term would be 0. So this thing is minus this thing, and also we know from continuity equation that del dot J plus partial rho by partial T is 0, and in time domain this becomes del dot J plus iota omega rho. So this del dot J is minus iota omega rho. So if I put for that, this becomes plus iota omega, let's take it out. And this thing, which is the first movement of charge density, is called the dipole moment of the current density. Okay? So the 0th movement of current density is total charge. The first movement of current density is dipole moment. The second movement is quadrupole moment, and so on. So let's define this thing as some P. So this thing is iota omega P. So A of R becomes mu naught minus iota K R 4 pi R. Or there's iota omega as well in the division. Here. So we found the the magnetic vector potential in terms of the 0th order movement of the current density, which is nothing but the dipole movement of the current density. So this is the, and if you have a dipole moment, as you have in one of the movement problem, if the current is such that it only has dipole moment and no other moment, so then if you find potential, it will immediately come out to be like this. And that's why you see, you begin studying about dipoles from, I don't know, from undergraduate, even perhaps in FSC, because they're not only important because dipole itself is important, but they're also important that an arbitrary current distribution has the first dominant term as the dipole term. The first term is the electric dipole term. Now once we have this vector potential, we know that B can be found as like this. अब इसमें हमने वहाँ पे लिखा हुआ है कि फॉर फील्ड में आप इसको आयोटा के से के एन से अप्रॉक्सीमेट कर सकते हैं, लेकिन इस केस में let me try to evaluate this curve exactly as it is for this thing. उसमें ये होगा कि ये B क्योंकि नियर फील्ड में भी वैलिड होगा और फार फील्ड में भी। अब असल में इसमें एक एतराज तो ये हो सकता है क्योंकि ये ए ऑलरेडी जो हमने लिखा हुआ है ये फार फील्ड है, तो फिर इसको डेल क्रॉस करें या के एन करें एक ही बात होनी चाहिए। लेकिन इट टर्न्स आउट कि इफ वी टेक डेल क्रॉस the result is valid in the near field as well. अगर तो technically once you have specialized this term to the far field, आप just far field में ही काम करें। लेकिन जो exact potential है अगर उसको भी हम approximate करें तो it turns out the first term still comes out to be this. So just for instructive purposes, let me evaluate this del cross as it is, जो कि आप आराम से कर सकते हैं क्योंकि del cross एक इस तरफ ये वाला और डिपेंडेंट चीज़ है, ये है, ये आराम से वैल्यूट हो जाएगा इस तरह से। जी जी हाँ जी, the other terms they don't come same but this one comes out. It's just an incidence, so let me just evaluate this thing as it is. So this is del cross P now del cross this thing is the del of this thing, the del of scalar function times the vector plus scalar and the cross of vector. Now this is 0 because this is a constant number, it's independent of R. This is the property of the current distribution itself and not the observation point. So this is 0. इसको अब आप expand कर सकते हैं by product rule plus this thing. इसका डेल माइनस आयोटा के बाहर आ जाएगा, r hat is actually n hat, तो ये डेल आ जाएगा माइनस 1 over r square n hat so we have B field as iota omega mu naught over 4 pi इस तरह E जो है उसको हम निकाल सकते हैं using Maxwell equation. So E, which is 1 over mu naught epsilon naught iota omega this thing, ये k को अगर हम लिखते हैं ओमेगा म्यू नॉट एप्सिलॉन नॉट स्क्वायर रूट, ओमेगा कैंसिल हो जाएगा, म्यू नॉट स्क्वायर रूट एक किससे कैंसिल हो जाएगा, c आ जाएगा, तो आयोटा आयोटा से we get माइनस c n plus p. So this gives us E as minus iota omega c mu naught 4 pi n cross p minus delta. So this is the electric field. Now, in the near zone, when R goes to 0, कौन सी टर्म डोमिनेट होगी, ये वाली या ये वाली? When R is small, which term is greater, this one or this one? This one, right? So B आ जाएगा आपका minus iota omega mu naught 4 pi r square n plus 1. And since this r is going to 0, this is 1. और e क्या आ जाएगा? So this term is dominant, so minus minus plus. Get iota omega. ये c की जगह पे लिख देते हैं 1 over mu naught epsilon naught square root. एक mu naught square root इससे कैंसिल हो जाएगा, mu naught square over epsilon square root आ जाएगा, z naught लिख देते हैं 4 pi. Let's see, are we going okay or is there trouble? Okay, so here I made a mistake because we used this far field approximation. Let's keep it as it is. तो अगर आप ये del cross का evaluate करें तो सब में एक 1 over r1 term आ गई. So this is actually far field. So let me write the total field, जो कि थोड़ा complicated है. आपको लिखने की जरूरत नहीं है, ये नोट्स में लिखूंगा सब. एक ये हम लिखे हैं द इलेक्ट्रिक फील्ड. वो पहला फार फील्ड में सिर्फ वैलिड था क्योंकि मैंने वो डेल को आयोटा के एन से रिप्लेस कर दिया. नहीं, ये अभी हमने करना है. अब इसमें देखिए, इसमें डोमिनेंट टर्म जो है वो ये है 1 over r cube पर when r goes to 0. So this will be the largest term. So the answer would be 1 over 4 pi r cube epsilon naught into this term is being multiplied with this thing. So 3 n hat n dot p minus p. So ये रिजल्ट आ गया. तो इन द नियर रूम when r is 0. अब इसमें देखें जो b है ये इलेक्ट्रिक फील्ड की रिस्पेक्ट से ऑलमोस्ट 0 है क्योंकि ये 1 over r square है और ये 1 over r cube है. So this is approximately 0. और ये जो रिजल्ट है, अगर आपको याद हो होमवर्क नंबर 1 या 2 में आपको एक स्टैटिक इलेक्ट्रिक डाइपोल का फील्ड निकालने को कहा गया था. दिस रिजल्ट इज एक्चुअली एग्जैक्टली द सेम. हो सकता है उसमें आपने सोल्यूशन में थीटा वगैरह की फॉर्म में लिखा हो, ठीक है, तो वो थीटा वगैरह की फॉर्म में आ जाता है. अगर लेट्स से पी डाइपोल आपका z एक्सिस के अलॉन्ग है, so this is your n hat vector, this is angle theta, so n dot p is p cosine theta, ठीक है. तो ये आपका z hat होगा, यहाँ पे r hat होगा. So this is the static electric dipole case. So किसी भी एंटीना का जो नियर फील्ड होता है उसको बाद का तो स्टैटिक zoom भी कहते हैं because the results correspond to the static electromagnetic case, either static electric or static magnetic. So near the antenna, it's as if the field is due to the static charge and current distributions. In the far zone के results आप चाहे यहाँ से approximate कर लें क्योंकि when r tends to infinity, ये टर्म भी स्मॉल है, ये भी स्मॉल है, सिर्फ ये टर्म 1/r वाली जो है वो लार्ज होगी। इसी तरह इसमें 1/r वाली टर्म लार्ज होगी। तो या आप जो डायरेक्ट पोटेंशियल का फार्मूला है उससे सिंपली आयोटा के n क्रॉस करके निकाल लें, ठीक है। तो दोनों सूत्रों से आप निकाल सकते हैं। सो फॉर जून इज this is B and E is और आपको जो होमवर्क में एक प्रॉब्लम दिया हुआ है उसके रिजल्ट जो डाइपोल का है वो एग्जैक्टली ये होना चाहिए, ठीक है, क्योंकि उसमें जस्ट आप डाइपोल को सॉल्व कर रहे हैं। इसमें ये रिजल्ट हमने निकाले हैं एज अ फर्स्ट टर्म इन द फील्ड्स ऑफ अ चार्ज डिस्ट्रीब्यूशन व्हिच इज नॉट इटसेल्फ जस्ट डाइपोल, उसके दूसरे मूवमेंट्स भी हैं लेकिन उसकी डाइपोल टर्म जो है वो ये है। और ये जो रिजल्ट्स है ये हमारे लिए इससे ज्यादा इंपॉर्टेंट है जब हम स्कैटरिंग को स्टडी करेंगे। वी विल अप्रॉक्सीमेट द current and charge distributions to be dipoles in scattering of particles. जो angular distribution है पावर की वो हम फाइंड कर सकते हैं उसी तरह से r square n hat like this and this is like this. So this is the angular distribution of the dipole term. आप अगर इसको कंपेयर करें स्मॉल डाइपोल के केस से, so you see they both have the same form. वो जो रिजल्ट है वो हमने अप्रोक्सीमेट किए थे लीनियर एंटीना को स्मॉल अज्यूम करके। सो व्हेन अ स्मॉल लीनियर एंटीना इज जस्ट अ डाइपोल, सो उस डाइपोल के रिजल्ट और इस डाइपोल के रिजल्ट दे आर वेरी सिमिलर इन द फॉर्म। इन दोनों में फर्क ये है कि वहां पे जब एंटीना स्मॉल किया है इट्स जस्ट अ डाइपोल, बट यहां पर दिस इज द डाइपोल टर्म ऑफ द जनरल field distribution due to a current। इस इसको distinguish कर रहे हैं। So a general radiating current has several terms in it. One of the term, and actually the dominant term, is the electric dipole term. It has the field distribution like a dipole. Excuse me। मैं अभी थोड़ी देर में अगर टाइम हुआ ना तो उस एंटीना को स्मॉल अज्यूम करके उसका ये जो डाइपोल टर्म है वो फाइंड करूंगा एंड देन वी विल पुट इन हियर, यू विल सी दैट देन इट बिकम्स इवन मोर सिमिलर। बट लेट्स प्रोसीड फर्दर फॉर द नेक्स्ट टर्म। नेक्स्ट टर्म इन द एक्सपेंशन n is equal to 1। n is equal to 1 टर्म कौन सी बनती है? वो दूसरे वाले बोर्ड पे लिखा हुआ है, इट इज इसमें आयोटा k था यहाँ पे, इसकी पावर 1 थी और नीचे 1 फैक्टोरियल था, सो 1, और यहाँ पे n डॉट r हैट की पावर 1 थी। अब हम देखते हैं कि ये इंटीग्रल क्या है। इसमें अगर आप देखें तो ये जो इसके अंदर टर्म लिखी हुई है ना, n डॉट r हैट J। थोड़ा सा आसानी के लिए इनपुट ब्रैकेट है, इसको हम लिख सकते हैं हाफ n dot r hat j of r plus n dot j r prime plus half r cross j cross n। लेट्स सी कि ये उसके बराबर आती है कि नहीं। ये A क्रॉस B क्रॉस C है, तो इसको आप इस तरह भी लिख सकते हैं, इस पार्ट को माइनस n क्रॉस r क्रॉस j, क्योंकि ये क्रॉस में अगर मैं ये टर्म पहले लिख दूं, क्योंकि A क्रॉस B क्रॉस C का फार्मूला हमने अक्सर याद किया था, सो ये B पहले आएगा, सो एक टर्म इसमें होगी r into n डॉट j, जो पहली टर्म आती है, तो वो माइनस के साथ आएगी, वो कौन सी टर्म बनती है, ये वाली, नहीं ये वाली बनेगी, और वैसे आ जाएगा n डॉट j माइनस के साथ, इसके साथ कैंसिल हो जाएगी। दूसरी टर्म इसमें कौन सी आएगी, j वैसे का वैसा और a डॉट b, तो दूसरी टर्म में नेगेटिव साइन होता है, वो नेगेटिव नेगेटिव प्लस, तो दूसरी टर्म बनी थी n डॉट r इंटू j, वो ये टर्म आ गई, ये हाफ है और एक इसका हाफ, हाफ एंड हाफ वन, वो टर्म आ गई। सो इसको एक्सपेंड करें तो दिस थिंग इज एग्जैक्टली इक्वल टू दैट। अब इसके अंदर मैंने इसको दो टर्म्स में ब्रेक किया, बिकॉज बोथ टर्म्स हैव डिफरेंट फिजिकल मीनिंग्स। जो ये वाली टर्म है, पहले मैं इसको देखूंगा, इसको हम स्टडी नहीं करेंगे, ठीक है, लेकिन इसके बारे में आपको बता दूंगा कि इसको रिप्रेजेंट करते हैं। लेट्स टेक दिस टर्म, इफ वी सब्स्टिट्यूट दिस थिंग इन प्लेस ऑफ दिस, we get a of r equal iota k mu naught 4 pi r potential minus iota k r half r prime cross j of r prime d क्यूब r प्राइम। ये देखें, ये जो n है ये r प्राइम पे डिपेंडेंट नहीं है, सो दिस कैन बी टेकन आउट ऑफ द इंटर। सो जस्ट द सेकंड टर्म, इस टर्म पे हम बाद में आएंगे, एग्री? दिस थिंग इज कॉल्ड द मैग्नेटिक डाइपोल मूवमेंट। M cross. So this is the vector potential due to a magnetic dipole, and this term is defined as a magnetic dipole. And when you have this magnetic dipole, मैं एक एग्जांपल से इस टर्म का आपको थोड़ा एग्जांपल दूंगा, आपको थोड़ा और आइडिया हो जाएगा कि this is really a magnetic dipole. So if we have this thing, अब ये जो पोटेंशियल है, बाय द वे, दिस अनफॉर्चुनेटली इज ओनली वैलिड इन फार फील्ड। जैसे मैंने कहा था ना वो डाइपोल वाले में, ये जो रिजल्ट आता है इंसिडेंटली, जो अगर एग्जैक्ट को एक्सपेंड करें तब भी वही आता है, लेकिन एग्जैक्ट को रिस्पॉन्ड करें तो फिर ये वाली टर्म उस तरह से नहीं आती। सो दिस इज ओनली वैलिड इन दैट फार फील्ड। सो इन द फार फील्ड व्हाट इज बी माइनस आयोटा के n cross a, so we get a squared mu naught 4 pi r n cross m cross n. So this is b, and what is e? E is 1 over iota omega mu naught epsilon naught del cross B, and del can be replaced with minus iota k n hat. So this is this. Iota cancel हो गया minus k omega mu naught epsilon naught. And what is n cross B? So इस चीज को यहाँ पे ले आते हैं, so this becomes k cube mu naught आ गया, 4 pi r आ गया, exponential minus iota k r आ गया, and then n cross m cross म्यू नॉट से कैंसिल हो गया। एक जो k है उसको अगर मैं अलग लिखूं तो वो ओमेगा म्यू नॉट एप्सिलॉन नॉट का स्क्वायर रूट बनेगा, ओमेगा से कैंसिल हो गया, सो माइनस k स्क्वायर, और एक एप्सिलॉन इससे कैंसिल तो म्यू ओवर एप्सिलॉन आ गया, z नॉट बन गया ओवर 4 pi r माइनस आयोटा k r। इसको इस तरह से ओपन कर रहे हैं, इमेजिन करें दिस इज a, दिस इज b एंड दिस इज योर c। सो पहली टर्म क्या आएगी जिसमें b हम वैसे लिखेंगे और a डॉट c होगा, और a डॉट c 0 है इस केस में, ठीक है, क्योंकि ये वेक्टर इस वेक्टर के परपेंडिकुलर है। सो दिस डॉट दिस इज 0, सो ये टर्म गई। दूसरी टर्म में c वैसे ही आ जाता है, and we have n dot n, so n dot n is 1, so this is just m cross n hat. So this is our E. So this is the electric field due to a magnetic dipole. जो पावर डिस्ट्रीब्यूशन है is r square, ये r से मल्टीप्लाई r square कैंसिल हो जाएगा, into n dot e cross b, so k square minus k4 mu naught z naught 4 pi square, so E क्रॉस B स्टार होगा, तो ये प्लस ही होता है, ये माइनस होता है, कैंसिल हो जाएंगे, एंड वी हैव देन दिस m क्रॉस n हैट क्रॉस n क्रॉस दिस ऑल डॉटेड विद n हैट। इसको अगर ओपन करें, इसको A समझ लें, इसको B समझ लें, इसको C समझ लें, तो पहली टर्म में C वैसे ही आएगा, और नहीं पहली में b वैसे आएगा, n आएगा, इसका इसके साथ डॉट होगा, तो ये बन जाएगा n हैट m क्रॉस n हैट स्क्वायर माइनस ये c वैसे आएगा और इसका इसके साथ डॉट होगा, ये डॉट 0 हो जाएगा क्योंकि ये वेक्टर इसके परपेंडिकुलर है, so the second term is gone। ये n डॉट n जो है ये 1 हो जाएगा, and we have the angular power distribution due to a magnetic dipole K4 mu naught Z naught 16 pi square m cross n hat square। But again, let's say suppose this is magnetic dipole is oriented along this direction, and this is n hat, let's say the angle between the two is theta. So what is m cross n? So we have minus mu naught Z naught 16 pi square K4, so ये m cross n आ जाएगा, इसकी मैग्नीट्यूड 1 है, इसकी मैग्नीट्यूड sin theta sin square theta। So इलेक्ट्रिक और मैग्नेटिक डाइपोल दोनों की पावर डिस्ट्रीब्यूशन सेम है। The only difference is just in the polarization of the emitted wave. जो इलेक्ट्रिक डाइपोल है उसका इलेक्ट्रिक फील्ड जो है उसकी डायरेक्शन ये है n क्रॉस p क्रॉस n, जो कि क्या बनती है बेसिकली पहले इसको माइनस कर उधर ले जाए n क्रॉस समझ लें तो दिस बिकम्स p माइनस p डॉट और p माइनस n हैट p कोसाइन थीटा। सो जब थीटा 0 होगा ये पॉइंट जो है दिस इज 1 and then n hat is z hat, so p minus p is 0, so there is no electric field actually. When theta is 90, ये जो point है this is 0 and p is in this direction, so this is p, so electric field जो है वो इस direction में है. So essentially the electric field is like this. ये electric field polarization है. जो magnetic field है इसका electric field अगर आप देखें ये वाला This is m cross n. So अगर ये magnetic dipole है, तो what is m cross n? M cross n is m sin theta, and the direction is perpendicular to both m and n. So ये अगर n है तो इसके क्रॉस प्रोडक्ट ये डायरेक्शन है, तो ये आपका अगर magnetic dipole पड़ा है तो इलेक्ट्रिक फील्ड है वो इस डायरेक्शन में, इस प्लेन में, उसका इलेक्ट्रिक फील्ड इस प्लेन में था इलेक्ट्रिक डाइपोल का। मैग्नेटिक डाइपोल का इलेक्ट्रिक फील्ड जो है वो इस परपेंडिकुलर प्लेन में। dp by d omega is defined as r square n dot pointing average. Any questions? Okay, let's come to the other term. ये जो टर्म है इस पे हम बात नहीं करेंगे मजीद। अगर इसको वैल्यूट करें तो बेसिकली इसको उसी तरह से सामने करंट डेंसिटी किया था, अगर मैनिपुलेट करें तो दिस बिकम्स समथिंग लाइक दिस n dot r round. So this becomes the second moment of current density. So this is called the quadrupole term. Electric quadrupole term. So electric quadrupole term and magnetic dipole term, they have the same behavior because this part is the same. But the pattern is more complicated, and usually this term is not that dominant. So the first two dominant terms are the magnetic dipole and the electric dipole. So let's take a couple of examples. पहले मैग्नेटिक डाइपोल की एग्जांपल देखें। Let's say you have a loop of current in XY plane. Okay, so the loop is in XY plane, and let's say its radius is a. अभी मैंने ऐसी करंट डिस्ट्रीब्यूशन चूज किया, इसका सिर्फ एक ही मूवमेंट है, एंड दैट्स द मैग्नेटिक डाइपोल मूवमेंट. द अदर मूवमेंट्स आर जीरो, यू कैन चेक, बट लेट मी इवैल्यूएट दिस मैग्नेटिक डाइपोल मूवमेंट जो हमने डिफाइन किया था यहाँ. सो दिस मैग्नेटिक डाइपोल मूवमेंट इज r cross this current distribution can be written in cylindrical coordinate as like this. करंट जो है वो phi यूनिट वेक्टर के अलॉन्ग है, phi यूनिट वेक्टर xy प्लेन में यूज आ रहा है. जो लूप है वो z is equal to 0 प्लेन में पड़ा हुआ है. At points other than z is equal to 0, the current is 0, and the current is non-zero only at r is equal to a. For all other values of R, the current is 0. So this is the way of defining a loop current, a circular loop current in cylindrical particles. So let me put it here. और जो इसमें फिर ये d cube R है, ये क्या होगा cylindrical quadrant? This is R, dr, d phi, dz. तो when z is equal to z, जो अगर आप z पे इंटीग्रेशन करें तो this integral will become half r prime at z is equal to 0 cross r dr d phi. z पर इंटीग्रेशन खत्म हो जाएगी इस डेल्टा फंक्शन की वजह से, और जो बाकी फंक्शन है उसमें आप z is equal to 0 पुट कर दें. अभी जो r पोजीशन वेक्टर है in the z is equal to 0 plane, this is oriented, this is given by simply r hat. ठीक है ना, ये जो पोजीशन वेक्टर है xy प्लेन के अंदर, this is directed along r hat, the cylindrical r hat, और इसकी मैग्नीट्यूड जो है वो r है. So this becomes half r hat cross phi hat delta of r minus a r dr d phi. ठीक है, ये देखिए लूप z इज इक्वल टू 0 प्लेन में पड़ा हुआ, ठीक है, और करंट और z इज इक्वल टू 0 प्लेन में करंट सिर्फ r इज इक्वल टू a पे है, बाकी जगह पे करंट 0, और करंट की मैग्नीट्यूड I है और करंट की डायरेक्शन जो है वो phi के अलावा. ठीक है, अब ये इंटीग्रल भी r पे भी आसानी से वैल्यूएट हो सकता है क्योंकि ये डेल्टा फंक्शन है, तो जो बाकी चीज है उसमें r की जगह पे आप a पुट कर दें तो ये a स्क्वायर हो जाएगा और इंटीग्रल सिर्फ बच गया phi के ऊपर, और r hat क्रॉस phi hat क्या होता है? So this is r hat, this is phi hat, और r क्रॉस phi होगा z. ठीक है, अब r से phi की तरफ कर्ल करें तो थंब z में पॉइंट करेगा, so this becomes z hat. So let's take z hat out. सिर्फ phi पे इंटीग्रेशन अब रह गई है. phi वेरी कर रहा है 0 to 2 pi I. So there was an I missing. I d phi. So phi पे इंटीग्रल 2 pi हो जाएगा, तो ये आ गया I z hat 2 pi आ गया, 2 से कैंसिल हो गया, we get pi a square, and this pi a square is the area of the loop. So I a. So इसका जो magnetic dipole moment है, this is this. Might have studied somewhere else that the magnetic moment of this is defined like this. So this is a special case definition. General definition जो है magnetic dipole moment की, it's this. So let's take a 5-minute quiz. Find the electric dipole moment of this current distribution. You have everything in front of you. The electric dipole moment of this current distribution. The definition of the electric dipole moment is here. So this thing relates the dipole moment. No, this is that is side equal to this. So P is 1 over iota omega of that impact.